Pseudo-label generation for agricultural robotics application is a joint work by Thomas Ciarfuglia, Ionut Motoi, Leonardo Saraceni and Daniele Nardi, all from the Sapienza University of Rome. The work has been developed in the context of the European-funded project Canopies that aims to develop a framework for human-robot interaction in the agricultural field. The test case is the table grape vineyard cultivation, with particular attention to automation of quality assessment, harvesting and pruning operations. This project sees the participation of 5 universities, 1 research center and 4 small and medium enterprises across 5 countries. This project has different goals. Some of them are a prerequisite for the others. Clearly, we need to build these robotic platforms and to develop a human-robot interaction framework, but to do so, a sophisticated perception layer is needed. In particular, perception is crucial for the detection and tracking of grape bunches that has to be harvested. Since the table grape is a soft fluid, this has to be done gently and precisely by the robot. We face some challenges related to this. One of them is the lack of properly labeled data of the type that can be found on the test field in Aprilia, Italy. The lack of labeled data is a common problem of agricultural systems. Sometimes a number of academic datasets exist for a specific cultivation, but often the covariate shift is considerable, as you can see in these images. Depending on the size of the farming company, it could be possible to invest in a data acquisition campaign, but this is often not the case for small-medium enterprises. In addition, we are considering the operation of a robotic agent that should be able to adapt to changing conditions across the day and the summer season. In the case of table grapes, specific datasets are not available, but there are a number of wine grapes datasets that can be used. However, there are considerable differences between the two, since the berry and bunch size are different, and the cultivation method, in the case of table grapes, requires the growth of the vine tree in a way to form a roof from which the bunches hang down. This creates a very different and mutable pattern of strong lights and deep shadows that increase the covariate shift problem. To quantify this covariate shift, initial experiments using YOLO and Mask-RCNN trained only on the source wine dataset showed a considerable decrease in performance on the target table grape dataset. Here you can see that the mean average precision decreases by more than 20 percentage points in all cases. Since collecting and labeled data from the field is simple in this scenario, we focus our solution on generating detection and segmentation labels automatically, leveraging the contextual information we could gather from the image capturing process. Here you can see the general overview of the system. The main idea is that the only input needed to the system is a video of the fruit collected with a simple smartphone or by the robot itself. The other hypothesis is that we are able to train a low-performance detector that we can use for the initial approximate labeling. Given that, the pseudo-label generation system is able to label the video with both new bounding boxes and segmentation masks, without human intervention. Going more in detail, the system is divided in 2 parts. The first one will label the video with new bounding boxes. This is done by extracting the initial bounding boxes with the source detector on specific keyframes, for example 1 every 5 frames. And then using classical feature extraction and matching, or extraction from motion, to estimate the position of bounding boxes in consecutive frames. Since with the movement, the illumination and occlusion conditions change rapidly under the canopy, the new samples will be different from the one in the keyframes. To obtain pseudo-mask for segmentation, we do the same trick of training an initial source segmentation network, and then we use it to create segmentation mask for the target data. Using this mask without modification would cause degraded performance due to the confirmation bias. We avoid this by using 2 strategies. The first one is to use the internal wiring of Mask-RCNN as it is used at inference time, to send to the segmentation head a specific bounding box instead of using the raw detection layers. Specifically, this bounding box is the one detected by the previously described after subsystem. The second strategy is to enrich the initial mask with the information coming from a different algorithm, in our case GrabCAD. Doing so, we are able to inject new external information to the pipeline that avoids the network to fall in the confirmation bias. Here you can see the whole system. The architecture is somehow complex, but the principle is simple once one understands the keys concepts behind it. This same system can be used for other fluid cultivation or even other object categories, since it's agnostic to them. Here you can see quantitative results of the test of the detector and segmentation networks trained on the new pseudo-labels. In the two upper tables, the target test data is different from the training data, since the second is collected with a reflex camera, while the first it's only the one coming from the initial smartphone video. Again, using mean average precision as a performance indicator, we see an increase of minimum 8 points for the detector and 16 points for the segmentation network. These two figures could be increased by adding more videos to the initial input. The code is ready to use and can be found at the repository link shown in this slide. You can try this system as an augmentation strategy for your next project. Please do not hesitate to contact me for further questions. Thank you for your attention.